All right, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park. Today is Friday, September the 26th, okay? And today we're going to be talking about reactions and why some things react and other things don't, okay? How do we initiate a chemical reaction? And how do we... why do some things react and other things not? So we're going to look at driving forces, and I'm actually going to give you an additional page to your notes today. Okay? All right, so let's review. I'm going to constantly be reviewing these things. Okay, so let's focus. Okay, let's have our notes out and we're focused. What are three, Micah, we're focused. What are three classes of matter? Go ahead, Anderson. Elements, compounds, and mixtures. So the three classes of I said it wrong. The three classes of matter are elements, compounds, and mixtures. Then we went to mixtures, and we had three types of mixtures. What are three types of mixtures? Good job, Graham. Solutions, colloids, and suspensions. What's the difference on those?
The size of the particles.
The size of the particles. A suspension is what did you say for it?
Cloudy.
Cloudy. Whereas a solution is always clear. Which one settles out due to gravity? Suspension. What keeps the solute particles suspended, ladies in the back? What keeps solute particles in the back? In the backs. See, I'm all mixed up. You got me rattled. What keeps the solute particles in a solution suspended and from keeping them from settling out? I heard somebody just say it.
Gravity.
Well, now gravity wants to pull them down. It's named after a person. Brownian motion. Okay? It's that random motion of the solvent molecules. Einstein kind of proved it, that the water molecules hit it. So we have our three types of mixtures. Now we have elements, and we have our three classes of elements. What are our three classes of elements? Say that again, Max.
Non-metals, metals, metals.
Non-metals, metals, and metalloids. We need to know where they are on the periodic table. Okay, and I skipped over one of the three phases of matter.
Solid, liquid, gas.
Solid, liquid, and gas. But the reality is there's more. What's the unique phase at the high temperatures? And the unique phase at the low temperatures? Bose-Einstein condensate. Okay, so it's all about the threes. So then yesterday we began talking about a physical change versus a chemical change. Physical properties, chemical properties. What physical properties can you tell me about this Dawn detergent?
Blue.
It's blue.
It's clear.
It's clear. Okay, it's liquid. Okay, what could we measure about it that we wouldn't have to change it at all? Volume. Okay. Density. Okay, we can measure the temperature. Okay, the mass of it. Which ones of those things that we just mentioned are dependent upon how much is present? Mass, volume. Does the density depend upon how much? No, because remember the alcohol lab that we did. Okay, so the ones that don't matter were called intensive physical properties. The ones that do matter are extensive. Okay, and then a chemical property, would this burn? Do you think it burned? What's the main ingredient in this? Water. So do you think it'll burn? No. Water doesn't burn. So chemical property is it probably doesn't burn. Okay? Probably doesn't react with an acid. Okay? It doesn't do much. Okay, so we need to be able to know that. So if I tear a piece of paper, is that a physical change or a chemical change? But if I burn the paper, what's the difference? Say it loud enough for everybody to hear.
One changes the property of the object, while the other one just changes size.
Okay? If you tear the paper, it's still paper, right? But if I burn the paper, is it paper anymore? No. Okay? Crud, I did it again. I left this on. Okay. All right. So today, well, lastly, to review, we talked about evidences, observations. How do we know a chemical change is taking place? If I mix water into the sugar, did anything happen? When I mixed water with sugar, okay, it dissolved, okay? But did you see any smoke? Did you see any fire? Did it change anything? But when I put the sulfuric acid that looked just like the water into the sugar, there was a color change, okay? What else? Smoke. Change, very much a change in odor. By the way, this is the only class that the room all kind of filled up for some reason with the smell more than others, okay? I think it's Dr. E's fault, okay? Did she not start it? What?
I did. What?
All right, yeah, all your comments are making it into the universe. Okay, so we have all of those evidences. Now, one of the ones that we talked about was the formation of a precipitate. What is a precipitate? I don't think I actually gave you a definition for that.
It's like a solid.
Okay, so a precipitate. Okay, that's going to be my abbreviation for a precipitate. Do I give that in the notes, the PPT? Okay. So what would be a good, I heard somebody say it, what? An insoluble solid that forms in a chemical reaction. You guys wrote that down for my words? Okay. An insoluble solid, you need to write it down if you didn't. An insoluble solid, and I'll spell insoluble for you. Insoluble solid formed in a chemical reaction. And the key is it's going to go from clear to what? Cloudy. Clear to cloudy. If it gets cloudy, we know that a solid got formed. It went from being a solution to a suspension. All right. So that's kind of where we are to date. That's everything that we kind of need to know up to this point. So today we want to talk about, well, how do we start a chemical reaction? There's going to be 5 ways to initiate, to start, or control the speed of a chemical reaction. Okay? First one is to heat it up. I mean, that's obvious. I mean, you put the steak on the grill. It speeds up the cooking process. Okay? How do I make paper burn? Light it on fire. Okay? You light it on fire. And so heating something up is the biggest way, and we're going to learn here why that is in just a little bit, but heating it up. And heating it up also increases the speed of the reaction. An increase of 10 degrees generally doubles the rate of the reaction. Okay? And all that's in the notes that you guys probably need to be following along with as we go through and do this. Okay? Now, the second one is light. And when we talk about light, now I gave you examples of this. What's an example of light initiating or causing a chemical reaction to occur? Okay, I put it out the magic window of science, right? That was the AgCl solid, which was white. When exposed to light, it went to, it was really just Ag solid, which was the gray, purplish kind of color, okay, in the solution. What's another one? This is hydrogen peroxide. Why do they have it in an opaque bottle, of one you can't see through? Because light causes hydrogen peroxide, H2O2 aqueous, exposed to light, decomposes into H2O plus O2 gas. Now I have to balance that equation. How do I balance that equation? What does it mean to balance it? Make the same number of atoms on both sides. The law of conservation of mass. In an ordinary chemical reaction, atoms are neither created nor destroyed. They just rearrange. Okay? So, I have two hydrogens. I have two hydrogens. Okay? You guys, come on. Okay? You don't have your notes with you today?
No, sir.
Okay? Two hydrogens, two hydrogens. Two oxygens, but I got three over here. Now, will this side ever be odd? Can I multiply anything by this by a 2 to get to an odd number? No. So I need to make this one even. So I'm going to put a 2 out in front of that to make that even. So now I have 4 oxygens. So I can put a 2 out here and get 4 oxygens. I have 4 hydrogens, but looky there, I have 4 hydrogens. Okay? So light will cause this reaction to occur. Another one that we talked about yesterday was photographic film. Now you guys really don't know what that is, but let me relate it this way. Have you ever seen in the movies where they have the dark room where they're developing the pictures, you know, like in a spy movie or something, where they're in this room? They always just have a red light and it has to be real dark while they're developing the film, because that photo paper is very light sensitive. And so they can use red light because, have you all ever heard of Roy G. Biv? The red, orange, yellow, green, blue, indigo, violet. Okay? Red is the lowest energy light. And so it doesn't affect the photo paper. So they can have a red light on in the room so they can see, but they have to be in the dark, no other colors, because it will affect the photographic film. So as they're developing that, they have to keep the lights out, because film is light sensitive. Light will initiate that chemical reaction. Okay? So that's the second one. A third one is electricity. And if you look in your notes, the word when you put electricity in is called electrolysis. Okay? Now, this is actually backwards because of the way I'm doing it, but, okay? Right here, I am putting electricity into water. And you can see the bubbles, and we're having a gas collect on each side. Now, I made a mistake and I let it go and I didn't fill it up right. And so, this actually is my hydrogen gas, and this is my oxygen gas, so it really should be more along these lines, where you have more hydrogen than you do oxygen. Okay? Why are we going to get more hydrogen than oxygen? Because what's the formula of water? H2O. So how much more hydrogen should I get than oxygen? Twice as much. Okay? So the volume over here, so this is hydrogen, and we can kind of prove that it's hydrogen by collecting it. Do I have my lighter? Where's my lighter? Playing with fire over here. I collect it. Okay? Oh, it's supposed to bark. Okay? Now it didn't bark because it's pure, but can you see the fogginess on the inside here? That's the hydrogen and the oxygen in the air remixing and going back to form water, and it's condensing on the glass. Okay? And so the hydrogen's burning. So this is hydrogen gas over here. This is your oxygen gas over here. We're decomposing the water. We're using electricity to decompose, to initiate a chemical reaction. Anytime you use electricity to do that, it's called electrolysis. I worked at Dow Chemical one summer in Plaquemine, Louisiana. It's just across the Mississippi River from Baton Rouge. Big, huge chemical plant. And they would get salt water from Napoleonville. That's a town down in South Louisiana, Napoleonville, but Louisiana is very French. And so they would have this big, they'd pipe it up, but then they had these huge electrical generators, and this is my non-official representation of electricity. My 2 lightning bolts. Okay, that's what that's supposed to be. Okay, don't go to college and use that because it doesn't mean anything. It's just my own thing. Okay, but this is electricity. And it decomposes it into Na plus ions, Cl minus, not Cl minus, OH minus ions, and then some hydrogen gas and chlorine gas. Okay, so they initiate it. So the reality is all the hydrogen and chlorine, that all is coming from water that's also reacting with it. Aqueous means there's water, so some of the water decomposes, that's where the hydrogen comes from. Okay, the chlorine comes from here, then the hydroxide and the sodium's left over from the other things. But this is huge. They make billions of tons of it every year. They use electricity to cause the chemical reaction. The fourth one is water. Please tell me that you've heard of Alka-Seltzer. Have you ever heard of Alka-Seltzer? Have you ever seen a commercial for Alka-Seltzer? Okay, the commercials for Alka-Seltzer are plop, plop, fizz, fizz, oh, what a relief it is. And then back when I was back in the 70s, they had this big fat guy come out and said, I can't believe I ate the whole thing. And then he's struggling with acid indigestion because he ate too much. And so then, plop, plop, fizz, fizz, oh, what a relief it is. Well, in this here, get some water for the plop, plop, fizz, fizz part. This right here, notice that it's in this waxy packaging because we don't want any water to get to the particles, okay? Because right now, in this solid, okay, everything that needs to react is there. But it can't react in the solid state because the molecules and atoms and ions are all held rigidly in place. They can't move. I think of it kind of like when I would go to a dance in high school. I'd ask a girl, I had a date, and she, I guess, reluctantly said yes. Okay, we would go and go to dinner or whatever, and we act like we like each other, and we're kind of together. But then when we got to the dance, and back in the day, we would actually dance facing each other, and we'd kind of do a little disco dance and all that. We didn't kind of dance the way that, not you guys, I know that you wouldn't dance this way, but the seniors, they sometimes do that front to back grinding dance that's kind of nasty and inappropriate for public, okay? Y'all know what I'm talking about, and it's just, I used to chaperone the dances, but then I'm not, I couldn't handle it, okay? Y'all know what I'm talking about, but somehow or other, when you get on the dance floor, it's all of a sudden okay, But, so we're just dancing together, but then somehow or other, as we're all on this dance floor, just kind of all mingling together, she kind of starts moseying over towards the guy that she wished had asked her to the dance, okay? And then they start dancing together, and then I just find myself that, hey, I'm just kind of here dancing alone. So then I just go to the punch bowl, okay? And so the dance floor acts as a medium to kind of break the things apart from one another. Okay, so the water is that great home wrecker. The water takes these that are stuck tightly together, and when you put them into water, they break apart into the individual ions. Okay? And now they're separated, and they're free to move around one another. And so now this one can leave the green and go to some other thing that it wants to be more attracted to. The water breaks them apart and allows them to have mobility so the atoms can rearrange. Because in an ordinary chemical reaction, atoms neither created nor destroyed, they simply rearrange. In the solid state, they're held too tightly in place, they can't rearrange. But the water, we say, plop, plop, fizz, fizz. Can you see it bubbling? Okay? You see it bubbling? What does that tell me? There's a reaction. So plop, plop, fizz, fizz, and then you drink it. Oh, what a relief it is that it neutralizes your stomach, excess stomach acid, and it makes you feel better. Okay? So we have a gas. Now, it's an antacid tablet. What does when you put ant in front of something mean? Not, or the opposite of. Okay? An antacid tablet is the opposite of an acid, which is what's the opposite of an acid? A base. It's really a base tablet, but nobody wants to say a base tablet, so they call it an antacid tablet. Okay? But it's the water, everything's in the solid state, but it can't react. You put it in the water, it's the great home wrecker. It can break the ions apart, so now they can rearrange and react. Water initiates. It's not really part of the reaction, it just provides the medium for the reaction to take place. Most of the time, if you saw all the reactions I did, they're all aqueous. They're already in water, so the ions have mobility, because solids generally won't react with one another. And then lastly is, she's not paying attention. A catalyst. What does a catalyst do? Okay, so write this in the blank. It speeds up a reaction without changing itself. It speeds up a reaction without changing itself. So we'll look at this exact same reaction. So I pour the peroxide into the cylinder. Okay? I put that in there. Right now, it is decomposing. The light is hitting it, and it's decomposing. It's undergoing this reaction. There is oxygen being formed. It's just super, super, super slow. It would take about a year or 2 years for all of this just sitting out to completely go to water and oxygen. But if you have some old peroxide sitting under your sink or in a cabinet somewhere, and then you get a scrape or a cut and you pour it on and nothing really happens, it's because it's decomposed and you're really just pouring water on your cut or your scrape. Because the shelf life, they say the shelf life for peroxide is about a year and a half. Then it really has lost its efficacy. It doesn't really work anymore because it's really pretty much just water now. So I need to speed this up. But again, I've done this already for you, so we'll just make it pretty. Okay, I like blue, so I'm going to do 2 blues. Okay, I didn't have any red. I don't know what happened to the red dye. I think RFK Jr. took it out of the schools. Okay. Okay, so now I have that. I need to have a little cleaning agent. Okay, but now I need a catalyst, so I'm going to have Ki. So I put Ki, some catalyst into here to speed up the reaction, and now, voila, whoa, okay? We're going a little crazy here, okay? Now, what is all this smoke? What is all this? What's the steam? So what does that mean about temperature? So does that mean it's endo or exothermic? Exothermic, an extremely exothermic reaction. Can you see how the catalyst maybe sped it up just a tad? Just a tad? Okay, where do I put a catalyst? Where do I put the catalyst in my equation? Over the arrow. So I'm going to say Ki is here. That's my catalyst. Okay? It's neither a reactant nor a product. It's not supposed to change itself. Now, because of the extreme heat, you can see some yellow. I don't know if you can just kind of see that some of that's yellow. That's some of the Ki breaking down into iodine because of the heat. And that's what, again, a chemical engineer, I remember going to Exxon when I was in Baton Rouge. I would take kids on a field trip to Exxon, and we'd go into the research and development area, and where they have the electron microscope, and the guy that was working on it at the time was looking at the catalyst that they use in their chemical reactions in the refining of oil. And he was looking because the catalyst kept breaking down. So they were trying to figure out what's causing the catalyst to break down, because the catalyst isn't supposed to change, it's supposed to be used over and over. But if they have to keep replacing the catalyst, that costs the company money. Okay, we want to figure out why is the catalyst breaking down? Is there a better catalyst that we can use that could maybe not break down? That's what a chemical engineer would do. The PhD chemist is analyzing it with the electron microscope, trying to figure out what. Then the chemical engineer is going to try and come in, well, what's a better process to maybe do exactly what we need to do, but maybe with a different catalyst that doesn't break down. That's how they all kind of work together. That's just kind of one very small example of chemistry and industry. Okay? So a catalyst, now listen, a catalyst will only speed up a reaction. It will not initiate a reaction. The reaction already has to be happening. It's simply going to speed it up. Does anybody know what the opposite of a catalyst would be? Catalyst speeds up. What do we call something that slows down? Very good. This man's on fire. What do you say over here? An inhibitor. Nitrogen in the air. There's 78% of the air is nitrogen. Nitrogen is an inhibitor. It slows things down. So this paper wants to burn, but most of the things hitting it are nitrogen, which doesn't burn with the paper, doesn't combine with the paper, making it burn. So it inhibits the process. Even when paper is burning, it's not going to burn as fast because still 78% of the collisions are with nitrogen, not oxygen. So the nitrogen is constantly getting in the way, slowing things down. It's inhibiting the reaction, slowing it down rather than speeding it up. Okay? All right. So those are ways in which we can initiate, start, or control a reaction. Heat does both. Heat will start a reaction, and it will make it go faster or slower. Okay? If you have your steak on the grill, you turn the grill on, you don't watch it, and it just catches on fire. Okay? Then your steak's going to cook way faster than you want it to. Okay? If it's down too low, then it takes too long to cook, and then it dries out. Okay? So the temperature, you can control the rate, but it also will start. Light, electrolysis, electricity, will only initiate a chemical reaction. A catalyst only does what? Speeds up a reaction. Okay? Water just will initiate. It'll help, mediate. It'll help cause the chemical reaction to occur. We need to look up some old Alka-Seltzer commercials. Plop, plop, fizz, fizz. Oh, what a relief. I can barely see over this big stack of books. Okay. So now, we want to get into some deep stuff. Now we want to ask the real question. Why do some things react and other things not? We have another page. This is a final page of notes. I think that's 4. Let's just see. I'm guessing.
Send me a message on Instagram.
Okay, everybody have a page? Okay, you can staple it later. All right.
I think I'm fine.
You literally missed when he was walking back. You just stayed over there.
All right, here we go.
Yeah, you're not paying attention. And he called you out.
Now, I'm over here.
It won't let me turn it down.
Here we go. Look. Okay, we just had a nice little mental break, so now we're ready to focus. I'm going to take some 1 molar, that's the concentration, some sulfuric acid, H2SO4, and I put that into a beaker. Okay? And when I put that into a beaker, and I put a penny into it, what happens? Did you see anything happening? Do we see any evidences of a chemical change at all? Any evidences of a chemical change? No bubbles, no changing color, the pennies just sitting in the acids. But if I take it's the same thing, and I take a piece of magnesium, okay, magnesium is element number 12, copper is number 29, so they're both metals, and I just take some magnesium, I've been working out, I just broke it with my bare hands, okay? And I put it in here, now, do we see anything happening?
Yeah.
What do you see?
Bubbles.
Bubbles. Okay, you can hear the bubbles, right? Okay, we can test the properties of those bubbles. Okay, they kind of pop a little bit. Okay. Ooh. Just trying to get a little bit more going. Okay, but the magnesium is obviously reacting with the acid. Just, I got it to pop in the other class. Let's see. Put a bigger piece. Go big and go home. It's definitely giving off something. Can you hear that now? So what does that mean about the gas that's being given off? It's flammable. It's hydrogen gas. Okay? So the question is, why did the magnesium react with the acid, but the copper not? There are two, what we call driving forces, two things that cause a chemical reaction to occur. And the first one is of lower energy. Reaction tendencies, forces that cause reactions to occur. What does spontaneously mean? Not necessarily at the same time.
Randomly.
Just randomly, all on its own. Spontaneously, all on its own. Okay? Without provocation. If I provoke something, that means I'm causing it to happen. I'm provoking that person to anger. Okay? Spontaneous just means all on its own. But it doesn't necessarily mean fast. Because believe it or not, this piece of paper right here is actually burning. This paper is burning. Okay? It's just burning extremely slow. This is my binder from college. It looks like it's been in a fire. It has not. It's been in this closet for 25 years. Okay? It's actually older than that. It's about 45 years old now. Okay? I take this out and I look at my diode and transistor characteristics from December 2nd, 1980. Okay? It looks like this paper, the edges, is all burned. My lab partner was Rick Burkholder. Okay? Okay? Now, I do want to make a point here. Gentlemen, okay, I'm very much a guy. But look at that. See how neat it is? Okay? It was a 9.5 out of 10. Okay, same thing as a 95. Hey, labeled, table was neat, not just kind of thrown together. Okay, I'm a sophomore in college. I'm not that much older than you guys. Okay, I'm just telling you, it is possible if you care about what you turn in. If you care, if you put your name on something to do something excellently, you can make it look good. Okay, you can learn how to have organized calculations. Okay, and do it right. Okay, I'm just saying, you just have to care. But this paper looks like it's on fire. This paper is burning ever so slowly. Why? It's occurring spontaneously. It's burning. Spontaneous doesn't mean fast. It just means all on its own. Just sitting in the cabinet, in the closet, it's burning just super slowly.
So like how fire do I have to like have a reactant that causes like the burn?
Okay?
What is the reactant?
Okay, what caused it to burst into flames? To see the fire? Glad you asked. Okay? Because if I look at my potential energy, and I look at my reaction progress, okay? This is going to be called an energy diagram. You guys do need to write this down. This is not oh my information. A reaction diagram. I'm going to start with the potential energy of my reactants. At some point, I really don't know. If I look at a piece of paper, I don't know what my reaction tendency, what my potential energy is. I just don't know. But this is going to be my reactants. They're going to have a certain amount of potential energy. Remember, that's not just the speed of the molecules, that's how strongly are the atoms bonded together. When atoms come together, they give off energy, but they have that certain built-in potential energy. Okay? How strongly are the atoms bonded together? Remember, breaking bonds, forming bonds is all potential energy. But to get the reaction started, every reaction has an energy barrier. And this is going to be for an exothermic reaction. Okay? And this is where my products are going to be. So when I'm looking at this piece of paper right here, okay, follow me. When I'm looking at this piece of paper, okay, I don't know how much potential energy there is. I don't know that. I just know it has some. But if I take it and I burn it, okay? Oops. I burn this piece of paper. Now we see fire. Okay? Okay? Whoa. Where's all that? The paper wasn't hot. There's way more fire than what I put into it. Where is all of that energy coming from? It's coming from the reaction of the paper plus oxygen. But to get it started, there's this energy barrier. This energy that we had to put in, that's what the match did. This is what we call EA, the energy of activation. Now, you can say it the other way too. You can say activation energy or the energy of activation, however you want to say it. Because I say E sub A, I call it the energy of activation, so we're saying E first. Okay? This is the energy needed to start a reaction. Energy needed to start a reaction, the energy of activation. So we got to put that in there. Now, I'm gonna answer your question here in just 1 second, but where did all the fire come from? Do the products have more or less energy than the reactants? Less, going down, right? So this right here, this difference is my delta H of the reaction. This is my heat of the reaction. The heat of the reaction. If I have an exothermic reaction, that means the products had less energy than the reactants. Well, if that energy was released, where did it go? To the air. This energy right here, that's your fire. That's what we see. That's the heat and the light, the fire that we see being given off is the difference in energy between the two. Now look, here's the confusing part with this. How can the reaction be losing heat, yet it's getting hot? Because we're talking, this delta H is potential energy. This delta H is the energy of the bonds breaking, bonds forming. Does a thermometer measure that? No. So as we go back and the ash now is back at room temperature, okay, the reactants lost heat as they went to products. Well, the law of conservation of energy says that energy is neither created nor destroyed, it just rearranges. So we're looking at the surroundings, the fire, all that heat. So if the reactants go to products go down, the surrounding has to go up. The energy Q loss has to equal negative Q gain, right? So the delta H is measuring the change in potential energy, which isn't measured by a thermometer, but we're observing the surroundings. That's why it's confusing, because they're opposite. Because the reaction is losing energy, but the surroundings is gaining energy. The surroundings are getting hot. That's what we see. That's the fire. That's what we feel. But the fire came from the fact that the reactants are losing energy as they're changing into products. Does that make sense? Are you following me on that? So it's that we have the system, the reaction, and we have the surroundings. In every case, we always have the actual reaction, and then we have what the reaction is taking place in, the surroundings. As the system loses energy, releases the energy, the surroundings gain the energy. The system goes down in potential energy, the surroundings go up in kinetic energy, they get hot. So what's an endothermic reaction? Well, before I even go there, we might have to wait for that. Let's answer this question. I'll stay over here. So what's going on here? Okay? How is this kind of burning slowly? What's the difference between that and a match? Well, in the air, what is temperature a measure of? Kinetic energy, there's an adjective in front of that. Average kinetic energy. That means some molecules are going slow, some are going fast, but there's an average speed for most of them. Okay? 78% of the molecules in the air are nitrogen, so 78% of the collisions with the paper are nitrogen. So 21% are oxygen. But there's an energy barrier that the reactants have to have enough energy to make it up and over the top. Well, at room temperature, only a very small fraction of the molecules have enough energy to make it up and over that hill. They're only going fast enough to kind of initiate, to start that reaction. So only 1 out of every bazillion or so oxygens that hit have enough energy and hit in the right way to actually react with the paper. So little by little, every once in a while, just by chance and circumstance, one hits it enough, it reacts. When I did my lab, this paper was this color. It's just over the years, one by one, oxygen molecules hit this, and they finally have enough energy to make it up over that hill, and then they react. So that's why they have to put the Declaration of Independence, enclose it and keep it from being exposed to light, keep it from being exposed to any air, because it will burn. It's burning, and you can see it just decomposing over time, because little by little, those high-speed molecules. Now, if I put this out in the desert somewhere where it's super hot, it's going to decompose faster. It's going to brown faster. If I take this up into Alaska, it's going to be much slower. Okay, but it's been in air conditioning. It's been at 72 degrees, okay, for 45 years now. And so as a result, just little by little, it's just burning. Little by little. So what happened when I do this? Okay? If I do it this way, okay, why is it going out? Where's all the heat going? Up and out. It's not going back into the reactant. So this heat that's being given off a little bit, I gave it some of them a push, okay, and they came down here, but any heat that's given off just went to the surroundings rather than back in. But if I do this, and then I let the heat go up, now, what do we know about the reaction? Much faster. Okay? Much faster, because now the heat's going back in, pushing more and more and more and more of the molecules up and over the hill. And with that, we'll end it and have a great weekend. Go Jags. Let's get a win tonight.